In section 7.3, we start looking at how we can use Lewis symbols and Lewis structures to describe the bonding in ionic and covalent compounds. So we're going to go through this in a couple of sections. We can lay out the basics of how we use Lewis symbols, and then we're going to go ultimately through systematic procedures for drawing complex Lewis structures for covalent compounds. So it's important to recognize that chemical bonds result from the interaction of electrons on different atoms, that the electrons that are going to be involved in bonding are those that we call the valence electrons. Another important thing to recognize is that some arrangements of electrons are very stable. That is, that they don't like to change. In particular, what we recognize is that the 8 valence electron arrangement, or what we call an octet, of the noble gases is extremely stable. So if elements can obtain an 8 valence electron arrangement through forming molecular or ionic bonds, then they're going to become very stable and reactions will cease at that point. So we're going to define a valence electron of a main group, that's one of those that's in the A groups, as just an electron that's in the outermost shell. And these electrons are always going to be in an S or P subshell. There is an American chemist by the name of Gilbert N. Lewis, and he developed a really cool system to illustrate the number of valence electrons that a main group element has. And it's really simple. What we do is we put one dot around the atom symbol for every valence electron that it has. And there's a few simple rules. I'm going to use carbon as an example here. We put one dot at each of the compass points until we have one dot at each of the positions, and only then do we begin to double up. Now, it doesn't matter where you start. You can start at the north position, or you can start at the east or west or south position. It doesn't matter, whatever you find most convenient. So fluorine, I want to put 7 valence electrons around it. We've got 1, 2, 3, 4, and now I start doubling up. And that's really it. And what you recognize fairly quickly is that all of those elements that are in group 1A have 1 valence electron. All of those elements that are in group 2A have 2 valence electrons. All of those elements that are in group 3A3 in 4 valence electrons in 5 valence electrons in 6 valence electrons, and so on. So the number of valence electrons that a main group element has is just equal to its group number. And we're going to use that a lot throughout this chapter. So for a main group element, the number of valence electrons is simply equal to the group number. So Gilbert and Lewis, he proposed that atoms tend to share electrons or transfer electrons so that each atom obtained a share of 8 valence electrons. That is, atoms form chemical bonds until they obtain a noble gas-like electron configuration. And that's called the octet rule. So how do we kind of combine this with the symbols? Well, it's really simple. For the non-metal atoms, these are the ones that like to form covalent bonds, the number of unpaired dots in an element's Lewis symbol indicates what we call its bonding capacity, and this is the number of bonds that it tends to form. So carbon in group 4A tends to form 4 bonds because it has 4 unpaired dots. Nitrogen in group 5A tends to form 3 bonds because it's got a bonding capacity of 3. Oxygen in group 6A tends to form 2 bonds. Fluorine in group 7A tends to form 1 bond. And neon, which is a noble gas, with a bonding capacity of 0, doesn't like to form chemical compounds. So this concept of bonding capacity and the octet rule is really, really powerful. Lewis symbols can also be used to help us understand the formation of ions and the formation of ionic compounds. So the metals that are the classic main group metals are those that are in group 1A, the alkali metals, and those that are in group 2A, the alkaline earth metals. And what these guys tend to do is they tend to lose their valence electrons, forming cations and in that way obtain a noble gas configuration. So sodium, which has 11 electrons, 10 of them are in the neon noble gas configuration, and then it has 1 electron in the 3s subshell. When it forms an ion, it tends to lose this 1 electron, leaving it with a neon arrangement. Magnesium has 12 electrons, 10 of them are in the neon noble gas configuration, and then it has 2 electrons in the 3s subshell. Magnesium likes to lose these two 3s electrons, forming an Mg2+ cation, leaving it with the neon electron configuration. Nonmetals, they tend to gain electrons to form negative ions that have a noble gas configuration. So if I look at fluorine, which has a total of 9 electrons, 2 of them are in the helium noble gas configuration, and then the remaining 7 are in the 2s and 2p subshells. What fluorine loves to do is gain an electron, complete the 2p subshell, and that leaves it with a neon electron configuration. Oxygen is in group 6A and it has 6 valence electrons. 2 of them are in the helium noble gas configuration, and then the remaining oxygen is in group 6A, has 6 valence electrons. It has 8 electrons total. 2 of them are in the helium noble gas configuration. The remaining 6 are in the 2s and 2p subshell. Oxygen loves to gain 2 electrons, completing the 2p subshell, leaving it with a noble gas configuration like neon. Now, that explains the formation of the individual ions. How do we explain the formation of an ionic compound, and how can we use Lewis diagrams to illustrate the formation of these compounds? What happens in the formation of an ionic compound is that metals transfer electrons to nonmetals to form the ionic compound, where every ion that is formed has a noble gas configuration. So if a sodium atom collides with a fluorine atom, what occurs is that the sodium atom transfers its 1 valence electron over to the fluorine. This gives a sodium cation that has a neon electron configuration and a fluoride anion that also has a neon electron configuration. Now, the sodium cation has a positive charge and the fluoride anion has a negative charge, so these ions become stuck to one another and we form the compound sodium fluoride. So everybody ends up with a noble gas configuration, but now these two ions are stuck to one another. The cost that they have to pay for obtaining this noble gas configuration is they now are bonded to the other ion. We can see another example here. Calcium in group 2A has 2 valence electrons. Oxygen in group 6A has 6 valence electrons. When a calcium atom collides with an oxygen atom, what's going to happen is the metal will transfer over its valence electrons. This results in the formation of a calcium ion, and calcium ion has 18 electrons in the argon configuration. The oxide ion that is formed has 10 electrons with the neon electron configuration, but the calcium ion is positively charged, the oxide ion is negatively charged. These ions are going to become stuck to one another, so again, and forming the compound calcium oxide. So again, every atom achieves a noble gas configuration, but they become stuck to one another. Okay, so that's how we can use Lewis structures to illustrate the formation of ionic compounds, and in particular to illustrate electron transfer between a metal and a non-metal to form an ionic compound. Lewis symbols can also be used to show how electrons are not transferred but shared in covalent molecules. So here we can see what happens when a hydrogen atom starts interacting with a fluorine atom. These guys are going to pair up their single electrons there. They're going to share those 2 electrons, and in that way what happens is that the hydrogen atom has 2 electrons like its noble gas helium, and the fluorine atom has 8 valence electrons like its noble gas neon. So both of these atoms obtain a noble gas octet. The only problem is they're stuck to one another because they have to share these 2 electrons. Now, a shared pair of electrons we commonly illustrate in chemistry as a single line, and this helps us kind of differentiate it from the electrons that are not being shared, that belong just to an individual atom. So by writing the shared pair of electrons as a line, we can tell that they are different from the other electrons that are present in our molecule. So we know that fluorine is always found in nature as F2 molecules, and we can kind of see why when we look at Lewis structures. When one fluorine atom collides with another fluorine atom, what's going to happen is they're going to share their unpaired electrons there, so that both of these guys end up with a noble gas octet. So now we have this fluorine atom's got 2, 4, 6, 8 electrons. This fluorine atom has 2, 4, 6, 8 electrons. Only thing is, they have to stick together because they both need these 2 electrons that are sitting halfway between the atoms. So we're going to replace those bonding electrons, that bonding pair of electrons, with a line to make it clear that they are different from these other electrons, which we call non-bonding electrons, that are located on each individual fluorine atom and are not being shared. You can see that the same thing would happen if we brought a bromine atom in contact with a fluorine atom. They're going to pair up their unpaired electrons, and so we end up with a bonding pair between the 2 atoms, and these, which we can illustrate with a line, and those atoms would become stuck to one another. Now, of course, most molecules involve more than 2 atoms, but we can see how larger molecules can also be built up in this way. So here we have 2 hydrogen atoms. That hydrogen's in group 1A has 1 valence electron. Interacting with an oxygen atom, oxygen's in group 6A has 6 valence electrons with 2 unpaired electrons here. So these guys are going to pair up, these guys are going to pair up, and that gives rise to the water molecule, where we have these 2 bonds between the hydrogen and the oxygen atoms, and then we have these 4 non-bonding electrons that are located on the oxygen. Here we go to a group 5 element, nitrogen. So nitrogen has 5 valence electrons. 3 of them are unpaired, so you can see that a nitrogen atom could pair up with 3 hydrogen atoms in this case, and then that gives a situation where we have our 3 bonded hydrogens, but then we have 2 non-bonding electrons on the nitrogen. And we can build up bigger molecules if we move into a central atom that has 4 valence electrons. It's possible for 2 atoms to share more than 2 electrons. What we've looked at so far are what we call single covalent bonds, where 2 electrons are being shared. But in some molecules, we will see double bonds, where we have 4 valence electrons that are being shared. And sometimes we will see triple bonds, where we have 6 valence electrons being shared. We don't observe quadruple bonds with 8 electrons being shared. So a classic example of a molecule where we have a triple bond is N2. And so in N2, we have a triple bond between the 2 nitrogen atoms, and this is very difficult to break, and that explains the relative lack of reactivity of N2, and we kind of observe that all over the place. In fact, N2 is so unreactive that we will often use it to maintain what we call an inert atmosphere. So if we don't want chemical reactions to occur with oxygen, we'll flush out all of the oxygen and replace it with N2, and that gives us a nice unreactive system. When 2 oxygen atoms come together, we end up with a molecule where we have 4 electrons being shared, so we have what we call a double bond between the 2 oxygen atoms. And because a double bond is weaker than a triple bond, we find that O2 is more reactive than N2. So what I should point out is that the weakest of our bonds are our single bonds, and the strongest of our bonds are our triple bonds. But if we look at the length of the bonds, as bonds get stronger, they get shorter. So that's worth keeping in mind. We're going to kind of come back to that later. So stronger equals shorter, weaker equals longer. Now you have to recognize that if you're going to form a double or a triple bond, what's often referred to as a multiple bond, then your atom has to have a bonding capacity of 2 or more. So that precludes the possibility of some types of atoms participating in this type of bonding. So for example, hydrogen only has 1 unpaired electron in its Lewis symbol, so hydrogen can only form single bonds. Hydrogen is always going to be on the edge of a molecule, and it's never going to be involved in double bonds or triple bonds. We see the same thing for the group 7a elements, the halogens. They only have 1 single dot there. And so these guys, again, they're going to be on the edge of molecules, normally forming a single bond. Now, there are sometimes exceptions to these things. We've been very careful to say that these are typical bonding patterns rather than them being absolute rules. But generally, we're going to find the halogens on the edge of molecules, and with hydrogen, it's going to go on the edge of a molecule as well, forming 1 bond. Now, if we look at the group 6a elements, this is the oxygen group, sometimes referred to as the chalcogens. What we see now is that we've got a bonding capacity of 2. So there's a couple of ways that we can utilize this. We can have 2 single bonds, or for the first time, we can have just 1 double bond. Now, when we move over to elements from group 5a, we now have a bonding capacity of 3, and we have more varieties of bonding that are possible for these types of elements. So we could have 1, 2, 3 single bonds, we could have a double and a single bond, or we could have a single triple bond, or just 1 triple bond. So we see a greater variety of bonding for the nitrogen group of elements because they have a greater bonding capacity. Okay, so if we move on over to group 4a, it's our last group of nonmetals, we see that the elements that are in this group have a bonding capacity of 4, and this gives the greatest variety of options as far as bonding is concerned. We can form 4 single bonds, we can form a double bond and 2 single bonds, we can form a triple bond and a single bond, or we can form 2 double bonds. So I should point out that should be just 1 single. There we go. Okay, so the bonding of carbon is very, very rich as a result of this, and that's why we have organic chemistry, which is focused on the compounds formed by carbon, because carbon is such a versatile element. And, we utilize this in biochemistry. Carbon lies at the heart of biochemistry because it's such a versatile atom. It can participate in all of these different types of bonding motifs. Okay, so that concludes the first part of section 7.3 that I would like to go through. And then there will be another video that focuses in great detail on very systematic procedures for drawing complex Lewis structures. We're going to be using this procedure for the remainder of the chapter, so I'm putting that in a video by itself.